right, so today's lesson's on empirical formulas, a chemical formula that shows the kind of atoms and their relative numbers in the most reduced form. Now, ionic compounds are always represented in empirical formula form because, remember, they exist as three-dimensional lattice structures as we see to the left, right? Now, crystals come in lots of different shapes, so you're not going to always have a certain number of sodium and a certain number of chlorine in a particular crystal. But what we can talk about is their relative numbers, right? I can have a crystal that's twice as big as this, but that repeating pattern has a certain ratio of sodium to chlorine. And so I'm not sure if you can see what that ratio is, but in fact, it is a 1-to-1 ratio. And so when we talk about ionic compounds, we always have to talk about the relative ratio because of those crystal structures. Now, something that's molecular can exist as a single molecule, and we don't have to talk about the empirical formula because, truthfully, for a molecule, the empirical formula can tell you what kind of compound it is, but not exactly what that compound is. So, for instance, there's a class of compounds called hydrocarbons. And perhaps you can look at an empirical formula and say, oh, this is a hydrocarbon. But it wouldn't tell you what hydrocarbon it is. We need the exact number. And so in this case, there are 3 carbons. There's 1, 2, 3, 4, 5, 6 hydrogens. I know that's hard for you to see, but I know what the structure looks like. And then I have a single oxygen. This is actually already in the reduced form. So for this molecular compound, its chemical formula or its molecular formula actually is an empirical formula. There are some hydrocarbons like C2H6, right? That's a type of hydrocarbon where there's 2 carbons and 6 hydrogens, also known as ethane. We could reduce this down to CH3, but that doesn't make sense when we try to draw the structure. We're like, a molecule can't look like that because carbon doesn't have a full octet in this form. And that would be true. But what we can see is it is a hydrocarbon. And so empirical formulas can help you with what kind of class of compound it is. But generally for a molecular compound, we'll keep it in the chemical formula or molecular formula form. Now, what do those subscripts stand for? Well, they can stand for a few things. If I was talking about this reaction where 2 atoms of hydrogen in a molecular form combines with a single atom of oxygen will make 1 molecule of water, right? But those numbers don't just represent number of atoms. We can just as easily say 2 moles of hydrogen will interact with 1 mole of oxygen to make 1 mole of water. Because remember, a mole is like a dozen, it's a counting value, right? So I could have just as easily said 2 dozen hydrogen, right, will react with 1 dozen oxygen to make 1 dozen water, but that doesn't, that's not a counting value that makes sense in chemistry because our numbers are so big, and so we use what's called the mole. So these subscripts can stand for moles or atoms. So another instance of that would be here, right? If we're talking about magnesium oxide, we can say 1 atom of magnesium will react with 1 atom of oxygen, right? Or we could say a mole of magnesium reacts with a mole of oxygen, or a dozen magnesium reacts with a dozen oxygen, right? Because all of these are counting values. Those subscripts stand for those different quantities, whether it's an atom, a dozen, or a mole. And that's going to be important when we're asked to find empirical formulas like this one. What's the empirical formula of a compound that has iron and oxygen in it? So we're essentially being tasked with finding the subscripts, right? What is the ratio of iron to oxygen? Now remember, we just got done saying that X and Y could be number of atoms, but it also could be number of moles. And so think about it. What would make the most sense? if we're giving grams of iron and oxygen, then which of these quantities would make the most sense to consider to find the ratio of X to Y? Yes, you guessed it. We should be talking about it in number of moles. And so that's what we're going to do. Our first step is to, yes, we are going to calculate the moles of each of these materials. So I'm going to take that 116.60 grams of iron, and I'm going to convert to moles, which is why we learned how to calculate moles first. Let's actually get the molar mass of iron from the periodic table. We see it's 55.85 grams for every 1 mole. And so we have 2.09 moles of iron. And now we look at the sample of oxygen, right? We have 33.40 grams of oxygen. And if we convert that into moles of oxygen, with each mole of oxygen coming in at 16 grams, 33.4 divided by that 16, and we get 2.09 moles of oxygen. Now, what we can't do is put 2.09 and 2.09, because remember, we're talking about the empirical formula. But what I hope you can see is this is a 1-to-1 ratio because they're equal. Now, if you couldn't see that it was a 1-to-1 ratio, what you would do is you would take the moles of one material and divide by the moles of the other material to see what that ratio is. In this case, we can see it is 1-to-1. And now we can write the empirical formula. Iron to oxide, 1 iron to 1 oxygen. All right, so let's take a look at another. If we're looking at another sample of iron combining with oxygen, in this case, again, we're asked to find the empirical formula. And so we take our grams of iron, for every 1 mole of iron, we just saw that it's 55.85 grams. And we're going to take that value and compare it to the moles of oxygen. And so we have 1.877 moles of iron. And now we go through that same process for the oxygen. And so we have 45.15 grams of oxygen. 1 mole of oxygen has a mass of 16 grams. And when we take that, we get 2.82 moles of oxygen. Now, some students would round this. They're like, oh, I'm going to round that to a 2 and this to a 3, and now I know my empirical formula. And in this case, that does work for you, but in a lot of cases, it doesn't. So actually, your next step should be creating that whole number ratio. And so what we do is we take the moles of one material and we divide by the moles of the other material. And what we get is we get a 1.5, which is the same thing as saying 1.5 over 1. It's like, okay, well, that's not a whole number, right? And so what we have to ask ourselves next is we need to consider what multiplier would turn them both into a whole number. That multiplier is 2. So if I multiply by 2 over 2, because we want to multiply by 1 so we're not changing the ratio itself, then we end up with a ratio of 3 to 2. 3 moles of oxygen to every 2 moles of iron. And now we can write the empirical formula. There's 2 irons for every 3 oxygens. Now some of you are like, Sparks, I know if I just rounded these values, I would have got the same answer. Yes, in this case you would have, but there's again, I caution you because there's going to be cases where that rounding does not work. Generally speaking, if you're off by um, 9/100ths or less, like 2.91 or 2.92 or 2.93, then you can round. But if you're off by more than a tenth, it is generally not considered prudent to round. And so I was off by 13/100ths here and off by 18/100ths here. So I didn't round. I did end up with the same answer, but again, there'll be plenty of cases where it's not. So if we review those steps, we can see that the first order of business is to convert to our grams into moles. After we've converted to moles, we multiply by, we create a whole number ratio by dividing the moles by the smallest value. So for instance, if I had 0.014 moles versus 0.007, if I divided 0.007 and 0.014, then I'd see that's a 2-to-1 ratio. Occasionally, when you simplify like that, you're not going to have a whole number ratio like we just saw, where we got a 1 to 1.5. And then we have to multiply by a multiplier. And in this case, that was 2 that would allow it to be whole numbers. Another instance of that is you might have a ratio of 1.17 to 1. You're like, oh, that's 1 to 1. No, we're off by 17/100ths from a whole number. So I have to multiply by some multiplier, and I just do a guess and check. 1.17, well, I know 2, 3, and 4 are not going to give me a whole number, so I'm going to start at 5 times 5. No, that's too far away from a whole number. 1.17 times 6. Oh, that gets me a whole number, 7.02. So my multiplier is 6, and that gets me this value to 7 and this value to 6. So if something had this as their ratio, now I can say x to x6, y7. All right, so one last example. What if we are given percentages, right? A compound is 73.9% mercury and 26.1% chlorine. And my question for you would be, does the amount of the material impact the ratio of the atoms? So if I had a cup of water versus a gallon of water versus a pool of water, does the amount of hydrogen compared to the amount of oxygen in the water change? And of course, the answer is no, it's consistent. So we can take whatever sample size we want. So if I'm given a compound that has percentages instead of masses, well, then I'm just going to assume a certain mass. Now, I like to assume 100 gram sample because when I apply the percentage to the 100 grams, it simply converts that percent into a mass. So it has the same numerical value. And I find that easier. But you can assume whatever mass you want. I have students that assume 1 gram and they'd apply that 73.9% to 1 gram. I like to deal with whole numbers, so or close to whole numbers, so that's why I'm going with this. 1 mole of mercury has a mass of 200.592 grams. And I would do the same for my chlorine. Well, with 73.9 gram sample divided by 200.59, we see that we have 0.368 moles of mercury. And now I'm going to go and do that for my chlorine. If I assume 100 grams and 26.1% of it is chlorine, then that means 26.1 grams is chlorine. I'm going to divide by the molar mass of chlorine, which is 35.45 grams. And I see that I have 0.736. Now, some of you can see the ratio, but again, if you can't, I would just take the smaller quantity and divide it into the larger quantity. and simplify. And what that simplifies is 2 over 1. And now I can write my formula, right? I have 1 mercury for every 2 fluorine. I hope that was helpful.